So, hi, I'm speaking to you tonight from Sherwood, Oregon, which is just in the country outside of Portland. And I'm here to talk to you because this is the 30th anniversary of the creation of the JavaScript programming language. JavaScript emerged in 1995 when the web was new, tiny, chaotic, in the early days of changing the world. Since then, JavaScript has become unimaginably successful. We are here, or at least you are, I'm here in my office, but we are here at JSConf because of the importance of modern JavaScript. We care about its future, but the future always depends upon the past. So we'll be better prepared to build the future of JavaScript if we understand how we got here. So let's explore some of the technical and social processes and design decisions that shaped modern JavaScript. So on December 4th, 1995, JavaScript was formally announced in a press release jointly issued by Netscape Communications Corporations and Sun Microsystem. But a lot had already happened before that announcement. The concepts and foundation technologies of the World Wide Web were developed from 1989 through 1991 by Tim Berners-Lee at CERN. His web technologies circulated within the high-energy physics community for a couple of years. However, they did not receive much attention outside that community until Mark Andreessen, an undergraduate student at the University of Illinois, along with Eric Binna, developed the Mosaic browser in 1992 and 1993. Mosaic was an easy to install, easy to use web client with a simpler graphic user interface. It essentially defined the web browser software category and popularized the web. Tim Berners-Lee's web technologies were originally designed to enable authoring and accessing statically constructed documents. The documents were declaratively described using HTML. An imperative programming language for document authors was neither provided nor desired at that time. By early 1994, commercial interests were scrambling to get on the web browser bandwagon by either licensing the Mosaic code or by building Mosaic-inspired browsers from scratch. Jim Clark, the founder of the workstation company Silicon Graphics, obtained venture funding and recruited Andreessen. In April 1994, they co-founded Netscape Communications Corporation. Netscape's goal was to replace Mosaic as the world's most popular browser. It developed from scratch Netscape Navigator, an enhanced next-generation Mosaic-like browser that was widely distributed starting in October 1994. By early 1995, Netscape Navigator was rapidly displacing Mosaic. In 1994, web pages were still primarily coded in simple declarative HTML. CSS and other advanced features were not yet available. Mark Andreessen felt that some sort of imperative scripting language was needed to make web pages more interactive. Early in 1995, Netscape developers started recruiting Brendan Eich to join Netscape, using the enticement, "Come put Scheme into the browser." Meanwhile, Sun Microsystems, the leading developer of workstation hardware and software, had decided to redirect its skunkworks Oak language from being a platform for smart appliances to supporting web development. They renamed it Java. In early 95, prior to any public announcement of Java, Sun and Netscape were discussing a strategic alliance to incorporate Java into the Netscape browser. In April, when Brendan Eich joined Netscape, this was all still being strategized, but it was assumed that Netscape would go forward with including Java in the next edition of Netscape, Netscape 2. There were still open issues concerning scripting. In addition to Java, did Netscape really need a scripting language for casual web developers? Did Netscape have the skills to create such a language? And they wanted to get it into the planned September Netscape 2 beta release. So Brendan was tasked with proving that he, and hence Netscape, could do all of this. Andreessen picked the code name Mocha for the project, although from the beginning, he hoped that the final name would be JavaScript. Over the course of 10 days, in the first half of May, Brendan designed the language and built its first implementation. At the end of the 10 days, he demonstrated it to the entire Netscape engineering staff. This is what he demoed. It's a browser console for evaluating Mocha code. Typing Mocha : into the browser's address bar opened the console. The bottom frame had a text box where Mocha statements could be typed. When the enter key was pressed, the statements were evaluated for effect upon the upper frame. In this example, the browser's alert function is called to display the value of an expression, something we've all probably done many times. About a week later, at Sun's official Java public announcement, Netscape was introduced as the first Java licensee, and that Java would be incorporated into Netscape's web browser. But Brendan's demo had been impressive enough that Netscape also decided to go ahead with Mocha as the scripting sidekick to Java. So what did Brendan actually build in those 10 days? Well, he built a parser and bytecode generator, a bytecode interpreter, a decompiler so he could recover the source code from the bytecodes, a basic library, and this Mocha console itself. So Brendan's marching orders were make it look like Java, but don't infringe upon Java's major features and strengths. Mocha should just be a Java sidekick, not an alternative to Java. In reality, that meant he borrowed C-like syntax, just like Java had. For other features, Brendan took inspiration from then common dynamic languages. A key decision inspired by Scheme was to treat functions as first-class values. So Brendan had less than 4 months to polish the Mocha prototype and incorporate it into the Netscape 2 beta release. He also had to integrate Mocha into Netscape's Livewire server product. And yes, maybe surprisingly, server-side JavaScript was there from the very beginning. But enabling interactive web pages required more than just a language with a REPL. So Mocha programmers needed APIs to dynamically inspect and manipulate the content of web pages. The APIs that Brendan developed for this purpose would eventually become known as DOM Level 0. Mocha code also needed to respond to user actions. Taking inspiration from Apple's HyperCard, Brendan developed an event loop execution model. When Mocha shipped with the Netscape 2 beta in September, Netscape named it Livewire. But that name was short-lived. On December 4th, 1995, Netscape and Sun held a joint press event where they officially announced JavaScript. The production version of Netscape 2 with both JavaScript 1.0 and Java 1.0 shipped March 18th, 1996. From today's perspective, JavaScript 1.0 was a very simple language. Rather than listing its features, it's actually more informative to list some of the features it did not have. It did not have do while, switch, or try catch finally statements. Also missing were break and continue to a label. It did not have type of, void, delete, in, instance of, or the triple equal operators. It didn't have nested function declarations, function expressions, or anonymous functions. Also absent were array literals, object literals, and regular expressions. It didn't even have a global binding for the identifier undefined, and it didn't have a garbage collector. So what about classes? Mocha needed objects enabled to interact with browser APIs and libraries built using Java, but it wasn't allowed to define classes. Sun required that Java was to be the only browser language for class definitions. Mocha was to be limited to being the consumer of objects that were instances of Java classes. Still, Brendan slipped in support for dynamically created objects that were essentially untyped property bags. He had also intended to include object prototype delegation, but that feature wasn't complete in time for the Netscape 2 feature freeze. During that summer, other groups within Netscape provided feedback about Mocha and made feature requests. Brendan tried to be accommodating, perhaps too much so. One of JavaScript's more confusing features is its automatic type conversion rules. Originally, Mocha's equal operator didn't do automatic type conversion. It operated more like modern triple equal. But one team member wanted automatic double equal type conversion so that web developers could write a number like 404 when testing a string valued HTTP status response, rather than having to remember to write the string literal quote 404 quote. A similar request led to automatic conversion of empty string values to 0. This provided a default numeric value for empty fields of HTML forms. There's a lesson here. You never know what's going to happen with a new technology. When working fast, be conservative about what features you include. It may become impossible to ever change or remove them. In early 1996, leading up to the JavaScript 1.0 release, Brendan shared in an interview his then current vision of JavaScript's role in web browsers. He said there was a need for interpreted from source, dynamically typed language that could orchestrate the interactions among HTML form elements and links, Java applets, plugins, and other components. He hoped that the audience for this language would consist of HTML authors who had some programming experience. Oh, okay, I didn't. He expected the language to be used to make pages a little smarter and more alive. For instances, make a click on a link load a different URL depending on the time of day. And he had relatively limited ambitions for JavaScript, hoping it would remain small but become ubiquitous on the web as a favored way for gluing HTML elements and actions on them together with Java applets and other components. He mentions Java a couple times, but overall, Java doesn't seem to have a unique role in this vision. Brendan built what he thought HTML authors needed. JavaScript was successful because it was designed to be a good companion to other early web technologies. It integrated with and empowered HTML. Java was ultimately unsuccessful in the browser because it was essentially a plug-in replacement for the web technologies. Java wasn't designed for HTML authors. It's fun to speculate how Brendan's little 1.0 scripting language might have been different in the absence of the Sun Netscape Java alliance. It probably wouldn't have ended up being Scheme or any other Lisp dialect. Perhaps, other than the name and the adoption of Java's confusing date objects, it wouldn't have been very different from what JavaScript actually became. Or as we will see, in a different alternative reality, it might have been basic. After the 1.0 release, Brendan continued to fix Mocha bugs and complete complete features, including prototypal inheritance that had not made the Netscape 2 feature freeze. This became JavaScript 1.1, which released with Netscape 3 in August 1996. Until the release of JavaScript 1.1, Brendan had been the only Netscape developer working full-time on JavaScript. JavaScript 1.1 was still based upon the prototype Mocha engine that was created during that 10 days in May. Brendan was frustrated and hampered by the technical debt that had accumulated. So in September 1996, he left the office and spent 2 weeks at home building an entirely new JavaScript engine. It would be suitable for a substantially enhanced 1.2 version of the language. He named the new engine SpiderMonkey. After Brendan returned to the office, a few additional developers were incrementally added to Netscape's JavaScript team. JavaScript 1.2, using the SpiderMonkey engine, was shipped in December 96 as the Netscape 4 beta. It added significant new features, including most of the previously mentioned missing features to the language. It even had a mark sweep garbage collector. In 1995, Mozilla was the Godzilla of the software industry. A major motivation for the Sun Netscape partnership was their joint belief that Microsoft would try to either crush or dominate the web browser market and technologies. Their concern was justified. Less than 9 months after the production release of Netscape 1, Mozilla shipped Internet Explorer 1.0 for MS-DOS. 3 months later, they followed with Internet Explorer 2 for Windows 95. And the day after the December Sun Netscape JavaScript announcement, Microsoft announced their intent to incorporate Visual Basic into Internet Explorer as its scripting language. However, shortly after the September release of the initial Netscape 2 beta, a few Microsoft engineers had started reverse engineering LiveScript. That's the initial beta version of JavaScript. In May 1996, Microsoft released a beta version of Internet Explorer 3 that included a scripting engine that supported both a dialect of BASIC and a dialect of JavaScript that they called JScript. JScript 1.0 was roughly feature comparable with Netscape's JavaScript 1.0. JScript 2.0 was comparable to JavaScript 1.1 and shipped in January 1997, and JScript 3.0 comparable with JavaScript 1.2 shipped in October 97. Throughout 1996, the Microsoft JScript team was complaining to Netscape that the lack of a JavaScript language specification made it difficult to create an interoperable implementation. Netscape and Sun, in their JavaScript announcement, had stated their intent to work with the W3C or the IETF to create a standard JavaScript specification. But the W3C wasn't interested in an imperative programming language companion for declarative HTML. And a language specification wasn't a good fit for the protocol focus of the IETF. Netscape still intended to develop a standard, but they needed to find a standards organization that could move quickly and not be dominated by Microsoft. They ultimately settled upon ECMA International, a Swiss-based standards organization that could fast-track standards to ISO, the International Standards Organization. ECMA billed itself as a low-overhead organization that allowed each standards development group to define its own processes. In early October 1996, ECMA issued a public announcement for an organizing meeting for a technical committee to draft a JavaScript standard. That meeting was held on November 21st and 22nd. This was the first meeting of what became known as ECMA TC39. There were 30 attendees representing 15 organizations. And why was it named TC39? Because it was ECMA's 39th technical committee. Both Netscape and Microsoft presented preliminary specifications that they had written specifically for the meeting. These documents are neither complete nor particularly precise. And there's lots of good stories behind that, which you can read about in the document I'll mention at the end of the talk here. But a portion of Microsoft's document used pseudocode algorithms to describe the evaluation semantics of various JavaScript features, while the Netscape document used prose descriptions. Here on the left is Netscape's prose description of JavaScript's prefix ++ increment operator. On the right is Microsoft's pseudocode specification for both prefix ++ and --. The attendees unexpectedly decided to use Microsoft's specification as their starting point. The fact that it was created using Microsoft Word, which was ECMA's preferred word processor, was a factor. But the group also liked the pseudocode-based specification style and wanted to use it. Even though both Netscape and Microsoft were already working on adding features beyond what was in JavaScript 1.1, the committee decided that the first edition should be limited to 1.1 functionality. They also decided that it should be a host platform independent language specification. Web-specific features such as the DOM APIs and the browser event loop would not be included in the specification. The goal was to have the first edition completed in time for approval by the ECMA General Assembly at its semi-annual meeting in June 1997. The first edition specification was drafted by a small technical working group that met weekly for the next few months. Various people attended some of these meetings, but the core contributors were Brendan Eich, Sean Kitzenberger, and Guy Still. Brendan represented the original design intent. Sean represented Microsoft's concerns and wrote most of the pseudocode algorithms. And Guy, as editor, pulled it all together into a coherent document. 3 principles guided the group: consensus, interoperability, and backwards compatibility. To this day, these principles remain key to JavaScript standards. Consensus meant that the group would attempt to make decisions that all participants favored, or at least found acceptable. Interoperability meant that JavaScript code should work identically on all JavaScript implementations. Achieving this required a detailed specification that captured all the nuances and edge cases of language features. When Guy had a question about how something was supposed to work, Brendan and Sean would write test cases and try them on Netscape's and Microsoft's implementations. If the results were identical, that would become the specified behavior. If there are differences in the results, the group discussed possible alternatives until they reached the consensus decision. Backwards compatibility meant that an implementation of the standard must not break existing code that was already interoperable between Netscape JavaScript and Microsoft JScript. For example, Brendan wanted to change the semantics of double equal comparison operator to eliminate its automatic type conversions. But Sean argued that it was too late. It would be unacceptable to break existing web pages that depended upon the original JavaScript equal semantics. However, JScript's triple equal operator would not break backwards compatibility, or it could be added and not break backwards compatibility. But as a new feature, triple equal didn't make it into the first edition of the standard, but by 1998, both Microsoft and Netscape had interoperable implementations of both double equal and triple equal in their browsers. So finding a name. The specification was sufficiently complete by June 97 for the ECMA General Assembly to approve it. the specification document was designated ECMA 262 because it would be ECMA's 262nd published standards. If you do any standards work, one of the things you'll discover is that standards organizations love to assign numbers to documents and then use those numbers and not their titles. At any rate, publication was delayed until September in order to make some editorial and technical corrections and to decide upon a non-trademarked name for the language to use within the specification. Sun had trademarked the name JavaScript and was unwilling to license its usage to ECMA. While the specification was being developed, a number of mostly bad alternative names were considered, but TC39 was unable to reach consensus on any of them. Within the specification draft, ECMAScript had been used as a placeholder for the ultimate choice. Finally, because it couldn't agree on anything better, TC39 decided just to use ECMAScript as the name of the language. So here we are. After publishing the first edition of ECMA 262, TC39 decided to work on a mostly editorial revision of the specification that could be republished as an ISO standard. This only became ECMA 262 second edition. There was also an almost complete turnover of TC39's technical participants at the end of 1997. Brendan stopped attending meetings in February 98, and he redirected his attention to being the technical lead of the Mozilla project, the effort to open source the Netscape browser source code. TC39 also started on a significant specification update that would add new features beyond those in JavaScript 1.1. Within TC39, this was initially called V2 for version 2, and resulted in the publication of ECMA 262 third edition in December 1999. Today, the JavaScript standards community refers to these early editions as ECMA 262 as ES1, ES2, and ES3. The development of ES1 through ES3 spanned a period of intense competition between Microsoft and Netscape, often called the first browser war. In spite of this, they were able to work together reasonably well together on these standards. It helped that TC39 only worked on the language specification and not on the more controversial and competitive browser DOM APIs. So I use the term classic JavaScript to refer to the version defined by ES3. For more than a decade, it was the version of JavaScript implemented in browsers. This was a period during which the AJAX style of web applications emerged. Classic JavaScript was also used in the initial releases of node.js. Brendan was the primary language designer via his implementation of Netscape JavaScript 1.0 through 1.3. However, Microsoft also made some feature contributions, such as the triple equal operator. TC39 mostly normalized differences between Netscape and Microsoft implementations. TC39's first foray into feature design came in ES3, and even there it was, for the most part, relatively minor features, except for exception handling, which was also added to ES3 and was developed within TC39. Browsers that implemented ES3 were quite interoperable with regards to things that were actually specified by the ES3 standard. But browser interoperability for DOM and the related APIs was not good. Most web developers thought of these APIs as just part of JavaScript, and hence they perceived that JavaScript had lots of interoperability issues. As work was nearing completion on ES3, TC39 was also thinking about what should come next as ES4. Java had found less adoption on web pages than expected, while its sidekick, JavaScript, had much more adoption than expected. Yet many TC39 participants still had Java envy. They thought JavaScript needed classes, a more sophisticated type system, modules, and other advanced features. In retrospect, many of those TC39 participants did not have a good appreciation of the actual needs of web developers, particularly with regards to backwards compatibility. Netscape's Walter Horwitz, who replaced Brendan on TC39, developed a design for what he called JavaScript 2.0 that incorporated many advanced features. But his position was that full backwards compatibility with classic JavaScript would be rather painful to achieve. So TC39 worked for over 4 years on ES4 as a from the grounds up redesign of JavaScript and its specification. This required trying to balance the radically different perspectives of Microsoft and Netscape. They both wanted a language with class-based nominal types. But Microsoft's design was influenced by its .NET platform team that preferred Java-like static type checking, while Netscape wanted to continue with runtime dynamic type checking. And neither worried very much about backwards compatibility with classic JavaScript. And there was little support for bringing either approach into browsers. In 1999, AOL had completed its acquisition of Netscape, and by 2002, Microsoft had won the browser wars with a 96% market share. Having won, Microsoft lost interest in further enhancing the browser as a platform. And AOL Netscape, with less than 3% market share, also stopped investing in the browser platform. So this first attempt at ES4 was abandoned in June 2003. However, Macromedia, the developer of the Flash browser plugin, was looking for a more powerful language for its developers. They wanted to use Sun's Java 2 Micro Edition, which was a version of Java designed for embedded systems, but their usage was not compatible with Sun's licensing terms for that technology. So instead, Macromedia decided to design and implement a new proprietary ActionScript 2 language by drawing upon the syntax and some of the other design work that had been done within TC39 for ES4. But then Macromedia and Flash were subsequently acquired by Adobe, which continued the development of ActionScript 3. In the late 90s and early 2000s, web standards seemed to be suffering from a sort of second system syndrome. ECMA TC39 had the ES4 efforts, and W3C had the XHTML effort. New people were involved who were dissatisfied with the original web technologies and decided they could do better by starting over from scratch, new language designs and new specifications, and of course, new implementations. As the first ES4 effort was winding down, a new group of people joined TC39 who thought that what JavaScript really needed was just language level support for XML processing. That effort produced 2 editions of an ECMAScript for XML specification, but it was not widely implemented. By June of 2004, the Mozilla project was finding unexpected success with its Firefox browser, and Brendan Eich decided it was time to re-engage with TC39 and try to get ES4 development moving forward again. But that effort was also ultimately unsuccessful. So Brendan tried to orchestrate a new ES4 design that built upon Adobe's ActionScript 3, along with new contributions from some academic CS researchers and a few Microsoft engineers that he had recruited into TC39. Excuse me, got some water there in my throat. Rather than using the previous pseudocode specification style, they decided to specify ES4 by building a reference implementation coded in the functional language standard ML of New Jersey. The new design incorporated many sophisticated and high-risk features, including a state-of-the-art structural type system with gradual type checking. Brendan tried to keep the project on track, but it was slow going. Starting in 2007, there was growing resistance to the new ES4 from a few of the TC39 members. There was concern that the new ES4 was either impractical or too different from classic JavaScript to be acceptable to either web developers or browser implementers. So I joined TC39 in early 1997 representing Microsoft and quickly became a vocal ES4 skeptic. The fact that Microsoft was suddenly objecting to the ES4 direction probably triggered some memories of the browser wars among some TC39 participants. And for a period, there was considerable disharmony within TC39. So why did TC39 spend most of 10 years doing the wrong things? I think it was a failure to understand and appreciate what Brendan calls browser game theory. The web platform is unusual in that it's a complex platform with multiple independent implementations and where applications are deployed as source code. This sets an extremely high interoperability bar among browser implementations. Douglas Crockford, the discoverer of JSON, described one problem as follows. With an ahead-of-time compiled language with multiple compiler implementations, C or C++, for example, an application developer gets to choose a specific deployment compiler and test using it before deploying to end users. With HTML and JavaScript web applications, it's the end user who chooses after deployment a quote compiler unquote when they choose to use a specific browser. So the developers don't necessarily get to test using what the end user is running. Additional web pages often remain accessible on the web, but unmaintained for many years. Yet users expect that accessible web pages should just keep working with new browsers. This makes browser vendors very conservative. They must support web reality, the web as it exists. Any unilateral language changes or extensions runs the risk of web page breakage that may drive users to other browsers. Advancement of web technologies requires design cooperation and agreement among multiple browsers with extreme attention to interoperability and backwards compatibility. And as basically don't break the web came out of this as a TC39 slogan. In 2007, when I started participating in TC39, Ajax-style web applications and frameworks that supported them were becoming quite popular. They were all being built using classic ES3 level JavaScript. But there were still remaining interoperability issues between browsers, and developers were asking for a variety of new JavaScript capabilities. Under Brendan's direction, Mozilla Firefox had added various new features to SpiderMonkey, but most had not been adopted by other browsers and hence weren't useful for interoperable web applications. At the time, TC39 was focused on designing ES4, but to me, that effort seemed to be in development hell, perpetually stuck at 6 months away from completion. We've probably all been there more than once. ES4 didn't have a traditional specification. Instead, it had a reference implementation that was an ML program that only its developers understood. It also had a bug tracker and a large informal wiki of ideas, incomplete feature proposals, and unsolved research problems. Backwards compatibility seemed to be at best a secondary consideration. Along with Doug Crockford, I proposed an ES4 alternative to reset back to the ES3 specification and start incrementally moving JavaScript forward via relatively small corrections and feature additions. This effort was initially called ES 3.1, and within TC39 became a separate working group operating in parallel with the ES4 effort. We started by identifying our goals and design principles we would apply. Our focus would be on improving interoperability while maximizing backwards compatibility. We would update the ES3 specification, rewriting sections to eliminate ambiguity and improve rigor and clarity. We're open to adding new features, particularly if they'd already been proven in browser JavaScript engines, but we wanted to avoid adding new syntax that might create forward compatibility problems for the then many deployed but infrequently updated web browsers. So remember, this is before evergreen browsers. So some cases, browsers would only be updated every 3 or 4 years. So the ES 3.1 working group spent much of 2007 analyzing the current state of interoperability among browser JavaScript engines. We wrote internal documents with titles like Mozilla extensions to ES3, JavaScript deviations from ES3, and implementation loopholes in ES3. Understanding the later was particularly important for improving interoperability. It had long been common practice for programming language specifications to leave out some details or to say some detail of the language semantics were undefined or could be defined by each implementation. The intent was to provide flexibility that allowed implementations to perform optimizations or to vary in how they dealt with unlikely edge cases. And it turned out that the ES3 ECMAScript specification had quite a few such loopholes that could be the source of interoperability problems. Improving interoperability in ES 3.1 was going to require elimination of most of those loopholes. We also discovered that the specification's use of pseudocode for defining the language's operational semantics, while very useful, had some shortcomings. There are still many uses of ambiguous prose descriptions for some of the core features that needed to be replaced with pseudocode. We also realized that the spec's use of an assembly language like pseudocode for describing complex semantics was error-prone for both specification authors and readers. The usability of the spec pseudocode language needed to be updated to at least catch up with the structured programming era. By January of 2008, the ES 3.1 working group had completed its research. We got the ES3 Microsoft Word document from the ECMA archives and turned it into an ES 3.1 working draft. We first updated it to correct errors that were listed in an unofficial ES3 errata and went to work removing specification loopholes, improving the pseudocode conventions, and resolving various ways that browsers' behaviors differed from each other and or the ES3 specification. At the time, there were 4 browsers that had some significant market share and TC39 participation. Microsoft Internet Explorer, Mozilla Firefox, Apple Safari, and Opera. The working group adopted a 3 out of 4 rule for resolving behavioral variations. If 3 out of 4 of those browsers had a common behavior for a detail of a feature, that behavior would be incorporated into the ES1 specification. If not, that feature detail was doomed to currently not be interoperable, which basically implies changing it wouldn't break anything that was interoperable. It could be modified or excluded from the specification. The working group was free to decide among the alternatives or to propose something new. So ES 3.1 added a handful of major new features. A set of object property level meta operations gave JS developers the ability to implement and emulate object models, such as the browser DOM, that previously could only be provided by a host platform. The new array functions that were originally available in Firefox and provided a more functional style of iteration over the array elements were added. JSON was already finding wide use, but depended upon either insecure use of eval or third-party JS libraries with various interoperable and incompatible APIs, various non-interoperable and hence incompatible APIs. New JSON functions provided a standard secure way or deserializing JSON format data. And finally, strict mode was designed as a way to clean up some of the oddities and edge cases that it carried forward from the original Mocha prototype, while still maintaining forward compatibility with existing code and deployed JS engines. It used a trick to allow ES 3.1 code to opt into additional parse time error checks. Strict code was enabled by using syntax that was already valid in all editions of ECMAScript, but had no runtime meaning. So strict mode code that parsed without error on an ES 3.1 engine would generally still run with the same behavior on pre-ES 3.1 JavaScript engines. The development of ES 3.1 proceeded through 2008, and in 2009, and into 2009, producing updated specification drafts every few weeks. Meantime, the ES4 effort was still stuck in development hell. In June of 2008, Adobe withdrew its support from the development of ES4, and that ended the project. The ES 3.1 effort was demonstrating a viable approach for maintaining and enhancing ECMAScript, which needed new features without requiring a complete reset. It was published as ECMAScript 5 in December 2009, exactly 10 years after ES3. In the course of writing the ES5 spec, the working group and their colleagues wrote hundreds of tests to understand where existing JavaScript engines deviated from the JavaScript specification. They tested JavaScript engine conformance to the spec's actual grammar productions and the steps of the pseudocode algorithms. These tests were ultimately formalized as Test 262. The ECMAScript implementation conformance test suite was the ultimate goal of covering every observable behavior specified by the ECMAScript specification. Not there yet, I don't think, but in 2025, Test 262 consists of over 50,000 individual test files. In parallel with the ES5 development, TC39 started a new project to develop a larger set of modern backwards compatible extensions for ECMAScript. It would build upon the ES5 specification, but could feature ideas borrowed from the ES4 project or elsewhere. Brendan Eich coined the code name Harmony for this new effort. It was sometimes also referred to as ES Next and ES6. The project was successful, but it took 7 years to produce the Harmony specification. It was officially published in June 2015. The termination of ES4 provided TC39 with its first opportunity since 1999 to start with a relatively clean slate as it planned an evolutionary path for JavaScript. No longer was TC39 thinking in terms of starting over to create a better language. Harmony was not constrained by previous decisions made during the ES4 effort, but it could still draw upon them. TC39 was constrained by decisions made a part of the ES5 project, but that work was generally in alignment with the direction Harmony was expected to take. Much of TC39 meeting times for the latter half of 2008 and much of 2009 was devoted to finishing ES5. This provided an opportunity for the entire community to grow comfortable with the ES5 specification as the starting point for Harmony. There was an eruption of new discussions about potential Harmony features. The workflow that developed was that new ideas would surface either on a public mailing list or at TC39 meetings. If a TC39 member thought an idea had merit, they could become its champion by writing a preliminary design or description of the feature and posting it on the Harmony Strawman wiki page. The Strawman proposals would be presented at a TC39 meeting, and depending on the committee's reaction, the idea would either be abandoned or the champion would iterate to refine the idea with the goal to achieve committee consensus needed to advance the straw man to accepted proposal status. Accepted proposals were expected to be included in the actual Harmony feature set. Most of 2009, 2010, and the first part of 2011, TC39 champions worked on developing strawman proposals. In April 2011, the Strawman wiki page, you see a bit of on the left here, this slide, had over 100 entries, and the accepted proposal page had 17 entries. The May 2011 committee meeting was devoted to triaging the strawman list and gaining consensus on remaining strawman proposals that would advance to Harmony accepted proposal status. By the end of the meeting, there were 44 accepted proposals. Some proposals represented important functionality. Some proposals were not yet really in a good shape, but they were important enough to not include them. So they were advanced to accepted status with the expectation that the current straw man would have to be significantly changed. So both modules and class proposals were given that treatment because modules and classes were definitely important for Harmony, but it took a long time to get the proposals right. With a set of accepted proposals in hand, it was time for a draft specification. As project editor, it was my job to craft the drafts. On June 22nd, 2011, I cloned the finished ES 5.1 spec and changed the cover title to say Draft Edition 6. I immediately started adding new material based on the May feature triage and other decisions that have been made by the committee over the previous 2 years. On July 12th, I posted for review the first of 38 working drafts of the specification. On April 14th, 2015, the last one was completed and submitted to the ECMA General Assembly, which approved it in June 2015 as ECMA 262 Edition 6. But its title was ECMAScript 2015 Language Specification. For each draft, I would take some of the accepted proposals and try to figure out how to incorporate the proposal into the specification. Most of the proposals weren't adequate for direct integration. Typically, I'd have to analyze how the features of the proposal would interact with other features and write the pseudocode that defined the semantics of the feature. Often features require significant changes to the pseudocode of other pre-existing features, and sometimes major restructuring of parts of the spec was required. For minor issues, I could exercise editorial discretion in resolving them, but for major issues, such as significant changes to a proposal's feature set, at the next TC31 meeting, I would lead a discussion on the problems and try to get committee consensus on resolving the issue. In parallel, a major design work was still needed to complete some features in the specification. In particular, the proposals for module and class declaration had major churn over the period of 2011 to 2014. Since there are many developers here today who use node.js, I should probably say something about why Harmony didn't just incorporate the Common JS module system? The short answer was that in 2009, both Harmony and Common JS were both brand new projects. Members of the Common JS team presented at the January 2009 TC31 meeting and a couple more times that year, but there are significant differences of technical perspective. A big one that the semantics of requiring a Common JS module would likely synchronously block the browser UI thread, while the module source was retrieved across the net. TC39 thought that would be unacceptable for browsers. Given sufficient time, perhaps the technical differences might have been resolved, but the main issue was that Common JS and Node.js teams were operating on a different timescale from TC39. Node wanted to ship that year and wanted to avoid getting bogged down in a multi-year committee effort. I don't have time to talk about all the features that were added in ECMAScript 2015 and subsequent editions, but they should be familiar to you. They are the modern JS features that you use every day. It is interesting to look at the actual page counts of the specs over time. ES1 and 2 only had about 100 pages. ES5 had about 250. ES 2015 had about 550, and the latest edition of ES 2025 has 834 pages. So it was 7 years from the start of the Harmony project to the publication of ES 2015. As it neared completion, it became clear to TC39 that the time span between ES5 and ES 2015 was too large. Some language feature proposals are small and uncontroversial changes that, given TC39 consensus, could ideally be incorporated into the ECMAScript specification within a few months. Others are large and controversial, requiring years to mature and find TC39 consensus. But the problem with large and frequent publication of new editions is that the time it takes for bug fixes and simple features to get into a published edition is the same as the time for the most complex new features. The result was the backlog of work for JS engine implementers, which further delayed availability of new features. So prior to the publication of Harmony, TC39 committed to following it with yearly updates to the ECMAScript specification. In June of every year, starting with 2015, a new revision of the specification has been published. Some years there's just only a few additions and bug fixes. Other years, major new features arrive. But all significant new features take more of a year to get into an ECMAScript specification. So features aren't initially targeted to initial release year. They get put in the specification when they're complete. Basically, what TC39 adopted is a release-trained software model. Every year, the features that have been, consensus has been released, that they're ready to go into the spec, are formatted into the actual specification document, and that becomes the next yearly release. To make this work, TC39 presented a process for how to deal with proposals, and it's currently a 6-stage process. The stages range from, here's a new idea that the committee might be interested in, to work is completed and ready to be included in the next edition. Each stage has entrance criteria and deliverables that must be produced, and stage advancement requires TC39 consensus. By the time a proposal reaches its final stage, it will have all the formal specification pros and pseudocode, test 262, conformance tests, and at least 2 shipping implementations. So ECMAScript 2025 incorporated 9 finished proposals. And so far, there are 3 finished proposals that are targeted for inclusion of ES 2026, but there might be more on the way. So wrapping up here, so after a trip through time, here we are again back in 2025, at a conference about the present and future of JavaScript. JS has evolved way beyond being just a tool for web pages that could orchestrate the interactions among HTML elements and other components. Today, in addition to web browsers, many other runtime platforms now host JavaScript. But the web is still and probably always will be the leading platform for JavaScript. If you're intrigued by ECMAScript standards process, you should visit the TC39 website, tc39.es, or scan that QR code. You'll find more information about the TC39 process and tools, meeting notes, draft specs, and proposals that are in the pipeline. So this talk is really just a roadmap of JavaScript's first decades. There wasn't time to get into the juicy technical and social details. Much of the material in this talk draws from a book-length paper that I and Brendan Ike wrote for ACM's 4th History of Programming Language Conference in 2020. If you're interested in digging deep into the details of what happened in those first decades, and in particular, what shenanigans went on about the first specs at the first TC39 meeting, it's open access, and you can access it using this QR code or just search for JavaScript the first 20 years. So thanks for sitting through a history class. I hope you enjoy the rest of this conference. And remember, don't break the web. So thank you.